sand and pea-sized stuff that just gets burnt up in the upper atmosphere or slowly drifts down through the atmosphere as it's stopped. But then we do see bigger ones, as I said. So the atmosphere is actually a very effective shield against very small fragments. It melts them, and then the melt droplets disappear off them, which we call a process of ablation, and it slows them down with the drag. The atmosphere is up to 100 kilometers high, and so there's a lot of slowing down that can happen. But bigger rocks have more momentum. Think of Ibn Etzebeth running into you, right? You're not going to stop him. So they are the lock forwards of the meteor world. And actually, it's estimated that between 10 and 50 meteorites land on the Earth's surface every day. Unfortunately, of course, 2/3 of our surface is water, so there are a lot of them sitting at the bottom of the ocean. So we get excited about the few that might end up on land. But actually, even though we have spread over the planet, there are a lot of places that are remote and a lot of places where these things land, so they don't necessarily land near us. How big are the fragments that then fall into the so-called bolide category? Well, they'll typically be meter size, so they'll be about 3 to 5 tons. Okay? They are dense, they would therefore be heavier than your average car, but they would not be bigger. So we said a car-sized object, but actually a car-massed object or more, but it actually turns out to be more like a motorcycle in terms of its size. There are also, as I will say later on, super bolides, and these actually start to put us into the dangerous realm, and I'll just mention that. So what happens is the bolide punches, the body punches through the upper atmosphere, which is thin, and as it comes down, it's getting into denser and denser atmosphere. Anyone who's belly flopped into a swimming pool knows that even though that's water, it stings. And so what we're going to find is that the body encounters more and more resistance at that hyper speed. And so it starts to vibrate, it starts to end up with stresses within it. And if there are pre-existing fractures in the body, or fractures that are made through that process, those may open, particularly as that air that can't get out of the way starts to push its way inside the body and heats up and therefore expands. And so ultimately there is this explosion. And that is the terminal blast. And that is actually, if you follow the narrative of the Cape St. Francis group, that's what Stephen said, Stephen saw, and Zoe managed to photograph the end part of that. So let's move on to that. So Tim has taken Zoe's video and broken it up into tiny fragments so we can study each point in time. The video starts at 8:50:49 seconds local time, which is 6:50:49 seconds universal time. And it starts after the main flare, which caught Stephen's attention. So we're looking at the breakup, the end part of this phase, which lasts only 2.8 seconds. So we've missed the other part, and we're hoping that there will be videos of that. We have some from particular angles, which Tim is now processing. And so what we see in this process is a series of parts of the original body slowly drifting apart, flaring, and then going out. And that's when they slow down enough that they're no longer being heated up by friction, and they enter dark flight. So what we then did was we looked at the eyewitness reports, and people very kindly sent in very detailed reports indicating their position, which way they were looking, what they were doing. You might have missed the bolide because you were chopping up your food, but you heard the sound that came later. And we also had the evidence that said people saw something, heard something, or felt something like a ground tremor, or some combination of those. And so these have been put together, and what we find, and then of course, there was the initial TV report that came out on the Sunday news, suggesting that objects may have splashed down in Jeffreys Bay. It turns out to be a bit of miscommunication, and so that was not what the eyewitness saw, and so it's helped us. We've received over 150 reports, and it's growing every day, and keep them coming. We would like to see what people have to say. The furthest sightings are over 600 kilometers to the north on a car at Petersburg, and 650 kilometers to the west, someone climbing a mountain in Ceres in the Western Cape. And when we start to put it all together, the external viewings are all sightings of the bolide, the bright light. But as we get closer to Gqeberha and west towards George, we find that there's sightings, but there's also sound, loud sound noises, sonic booms in the air, and violent vibrations or moderately violent vibrations. People could feel the ground trembling. And so from that, we conclude that the focus of the event was in this region between Gqeberha and George, and that the body from the eyewitness accounts was moving towards the east-northeast or northeast from essentially the coastline, moving inland. And we'll see in a moment that the main mass detonated. This is fixed by NASA and programs and international programs. The main mass detonated over the Great Winterhoek Mountains that are west-northwest of Gqeberha. The last thing I want to do is point out this point up here, Boshoff. It's not a viewing point, but I want you to mark that line, because at Boshoff we have an infrasound station, one of the 60 around the world, that monitors the movement of high-speed objects into the upper atmosphere. And it's primarily part of the Cold War defense strategy and monitoring strategy to look for missiles coming through the upper atmosphere. But thankfully, it's never been need to be used for that, and it has been turned to study of these bolides coming in. So remember that infrasound would be a sound that is lower than the human hearing threshold, and it can travel great distances, so it's very useful. So elephants use it to communicate, for instance. Our station, I47ZA, is near Kimberley at Boshoff, and it's just under 600 kilometers from Gqeberha. And what we see at the station, here is the station record with the time indicated based on universal time, which is 2 hours behind us. And you notice that it's all okay until this point over here at 7:22 or 9:22 local time. So isn't that a bit late? Well, the problem is you've got to remember that sound does not travel as fast as light. Sound is going to take time. This is how we work out how close we are to a lightning strike. We time the distance between the strike, the light, and the sound that is caused by that violent strike. And so it takes 29 minutes for sound to travel roughly 590, 600 kilometers at 1/3 of a kilometer per second. And so if we back calculate that, we see that in fact it fits an event at roughly 8:53 local time. Remember Zoe's video, roughly 8:51. So give or take a little bit of variation in the sound. It's got 29 minutes to mess with the atmosphere. We're on track. And what is even more important is that when you plot, because the station actually works out the direction from which that sound came, the cluster of readings all sits in the direction. Remember, this is the direction towards Gqeberha and the area to the west. So it sits in that vector between 176 and 199 degrees, which is essentially south to south-southwest. So the infrasound station locally was able to confirm there was this massive event, if we ever had any doubt, and to indicate what was there. But can we go better? And here we turn to an organization called the Center for Near-Earth Object Studies, CNEOS, that reports. It took 2 days for it to finalize its report, and it came up with a table. You can see the table along the bottom. It gives the coordinates, and then it tells us some of the details. And it worked out that that object was traveling at this cosmic velocity of 20 kilometers per second. The energy release was equivalent to 92 tons of TNT. So if you find an average sized room of 4 by 4 by 4 meters, I know our ceilings aren't 4 meters high, but this one's probably 4 meters high, you would pile that into place, and that's how much energy was released by this event. The disruption occurred quite high, at 38 kilometers altitude. So what people were seeing for a brief moment, I know we see stars, but on a brief moment you were seeing up to 80 kilometers to 40 kilometers above the land surface, not just behind the clouds, a long, long way up. This was the 20th bolide reported on the site in 2024. And its diameter, as I said, we thought car size. We were having a look at the images, and it was a thumbsuck at that point. But it'll be slightly smaller than that, less than 1.5 meters, probably about 1 meter cubed, so about this size. And there it sits. It is on the database. You can look it up. There's the little dot sitting there off Gqeberha. So what else do we have? Well, actually, there are seismic stations that are monitored by the Council for Geoscience all over South Africa. And there are some to the west of Gqeberha. And here's the station unveil, which lies about 100 kilometers to the west of the city. And what we see happening there is that again, at universal coordinated time, we have an event just before what would be 8:55 a.m. our time. There it is, that very sharp spike, and a lot of activity just immediately after that. So the station is shaking. There's a tremor. That tremor has multiple sources. Initially, what is happening is because this object is traveling much faster than the speed of sound, it creates what we call a Mach cone. You know about Mach 1, Mach 2, and this is called breaking the sound barrier. So direct sound waves hit the station from the air, and that's what probably gives this sharp bounce. In addition, the explosion, the terminal blast at 38 kilometers, would have radiated out a massive explosion that could then have been picked up by the station. And finally, some of those sonic waves hit the ground, causing them to vibrate, and the vibrations travel along the ground to the sensors. So we have all of this here. We notice that the event happens at the station at roughly 2 minutes after what was recorded on Zoe's video. And so we can estimate that it was about 40 kilometers from the station, which is remarkably similar to the detonation height of 38 kilometers, suggesting that the bolide probably passed very close to the Esville station. And so to conclude then, the local and international sensor instruments that are highly sensitive have corroborated each other and the eyewitness accounts that the sonic booms and the sounds like thunder that people heard, the ground tremors that they felt, even though they are delayed, can be explained as a result of this high altitude bolide. And what we're seeing is proof that the bolide was actually very high in the atmosphere, meaning that the sound energy had to take a long time to get to the ground, whereas the light energy was essentially instantaneous. So it now gives me pleasure. That's the background. Now we get to the real part that people are here, and Nicholas will introduce.
Hi, let me introduce Dr. Dion van Niekerk from Rhodes University, who is going to share with us some of these initial observations on the sample that we found last week.
Thanks, Nicholas. Where are we? Good morning. How do I forward this? I'll tease you a little bit first. You know, it takes a special person to study rocks. Geologists are frequently at the brunt of jokes. But, you know, if you consider that meteorites are the only physical pieces of the world beyond our atmosphere, of the universe, that we can actually hold and touch, you know, it's really cool being able to study these rocks. So they might look boring, but it's very exciting. The point I want to bring home on this slide is that these are some of the fragments of the meteorites. There are 5 fragments in total. The meteorite broke up when it hit the ground. There are 2. These 2 are the same on the left and right at the top. Those are part of the same fragment, and the 2 at the bottom. So we're looking at 1 fragment at the top and 1 fragment at the bottom, just to give you a sense of scale and how big they are. They are small, actually, you know. It's 90 grams total mass. This top one, you can see it's 4 centimeters. This bottom one's about 3 centimeters. And as Professor Gibson was saying, you know, we're looking at a much smaller than car-sized. So it is incredible that somebody actually was at the location where these rocks fell. You know, there might be more rocks out there that we're going to look for, but it really is a needle in a haystack. You know, there isn't a lot of this material that reaches us, and it's an incredible contribution to science. So this is a close-up of one of the fragments I showed previously. I'm putting out the fusion crust here. So you'll see it's black. Dr. Dodd was referring to the meteorongs, and she showed a slide of some of the animal scat and a rock with a black crust on it, a patina. And this is why people can confuse real meteorites with false meteorites or other rocks and things. When we look for meteorites, we commonly look for this fusion crust. This is basically a molten outer portion of the rock. As it's coming through the atmosphere, it's heating up, it's melting, and then it cools quickly and it forms this black crust. So this is a cue to us when we're looking for meteorites that we should be paying attention to whatever rock is lying around. This is the other fragment, and what I'm pointing out here is you can see there is also fusion crust here, but here we actually see an interior part of the meteorite where it broke open. So if this side was facing up, you wouldn't necessarily recognize this as a meteorite, but because it's got that fusion crust on it, you would recognize that. So getting into some of the nitty-gritty here, I have to stress that these are preliminary observations. You know, we've had these rocks for only a few days, and so usually when we start describing them, we give it a fancy term. We say we're describing them macroscopically, which basically means we're eyeballing them. You know, this is the first start to any scientific investigation, is just to get an initial idea of what we're working with, and to plan our more detailed analyses from there. So what we can tell here, observation-wise, is importantly that there are no chondritic textures. So Professor Gibson was referring earlier to chondrite meteorites, which dominate the meteorite collections. And it's important to note that there are no chondrules or chondritic textures or anything associated with chondrites visible in these rocks macroscopically. So from that, we can immediately say that we think we're looking at an achondrite. There's also no metal. You get a lot of iron meteorites or stony iron meteorites that contain metal. There's no metal in this. You can observe a light gray matrix here. This is really microscopic, so we'll have to look at that closer later on, as one of my colleagues will explain later on. But this is a bit of a brecciated texture because you've got that fine-grained matrix, and then you've got these clasts, big clasts of different sizes in there, and we're not sure at this point what it is. We really have to look at that under a microscope. These could be pieces of other rock fragments from the parent body of the asteroid, for example. Importantly, we can see some green crystals here. So those give us a clue that they might be rich in magnesium and iron, silicate oxides. And that is really the bulk of what we can tell from the sample just by looking at this. But we can deduce a lot from that. If we compare images of these samples and the descriptions with other meteorites that have been found and classified, we can make a preliminary conclusion that these are fragments of an HED meteorite. So, sorry, my pointer went away. So, HED stands for Howardite, Eucrite, Diogenite. Those are three different meteorite types that are associated. They're achondrites. And the HED meteorites come from a differentiated parent body. Now, what that means is that the parent body in space underwent melting. So let's say, for example, simplistically, you start with a very primitive rock, like a chondrite, and you then melt that rock. That asteroid will start differentiating into different layers. Basically, you'll have magma or lava, or a magma ocean that will separate into layers. And it's very important because old meteorites like this must have formed very early in the history of the solar system to have melted. And we suspect they may have incorporated the short-lived nuclide aluminum-26. So this is just a schematic representation of what a differentiated body would look like. So you're basically taking a primitive body, you're melting it because of the heat generated by the short-lived nuclides. And then in this pool of magma, basically, there are some crystals and minerals that will crystallize first thermodynamically, and they will basically sink towards the center. and some of the later crystallized minerals will form shells higher up in the crust of the minor body. And you can even have volcanism on these bodies. So think of these layers as having crystallized from pools of lava. That's a good way to think of it. So the HEDs, if we look at the D, that stands for diogenite. And those represent shallow crustal or upper mantle cumulates that are rich in magnesium iron minerals, for example, those green crystals you saw. So on the little schematic there at the top right, that would be, say, represented by the second layer from the top down, perhaps, the greenish layer below the light layer. The eucrites would be surface lavas and or shallow magma, and they're rich in calcium minerals. So there's a compositional difference between these meteorites that we can pick up through further scientific analysis, and they would represent, they would be on the surface of the minor body. And then the howardites, they represent regolith breccias. So they are mixtures of eucrites and diogenites that are produced by impact processes on the minor body surface. So as you're impacting and creating craters, you're mixing things up. And so excavating deep craters and mixing things, so you mix the eucrites and the diogenites and keep them on the surface. So these are really messy rocks. They're breccias. They're mixtures of all kinds of components of things that have been busted up. So it's important to note that while the HEDs as a group are relatively common on Earth, the howardites and diogenites are among the rarest of observed falls. So we suspect that this meteorite that we have might be a howardite or diogenite, but really these rocks are very tricky, and it's only when you get down to the microscopic scale that you can be definitive about them. So I say that with reservation. Now, another cool thing about the HEDs is that many decades ago, they were spectroscopically linked through visible and infrared spectra observations of rocks in the laboratory and in space. They were linked to the asteroid 4 Vesta. So HED meteorites have similar compositional optical spectra to an asteroid in space. So if you think about that, that's quite incredible, that you can have a piece of rock in the lab, you can measure it, and then you can telescopically measure something in space amongst all the bodies in space and say, hey, these two things are remarkably similar. So for a long time, the scientific community has suspected that the HEDs come from the asteroid Vesta. So that is an image of Vesta. So it's the second largest asteroid, I believe. It's about 530 kilometers across. It resides in the main asteroid belt, which is about 2 to 3 astronomical units out in the solar system. And you can see a body like this, it's seen a lot of impact activity. So I was referring to the howardites. Well, this is how these things form. There's lots of deep excavated craters. One of the deepest excavated crater is in the south, and it is believed that the source of the HED meteorites that we find on Earth actually comes from a big crater, perhaps like in the south. So all of this, including this image, courtesy of a very convenient NASA space mission to the asteroid 4 Vesta, and this mission is called Dawn. I believe at the moment it's at Ceres. I speak under correction, but Dawn visited 4 Vesta for several years, 2011 to 2018, after I think maybe a long journey in space. I think it was in space 4 years on its way to Vesta, then it got there. And it basically confirmed the long-held hypothesis that the HEDs are geochemically related to that asteroid. It is dynamically difficult to get HED meteorites off Vesta itself. However, there are other asteroids that are related to Vesta, called the Vestoids or Vestoid family, and it is believed that they represent material that's been excavated from these deep craters on Vesta, and they lie closer to dynamically unstable regions in the asteroid belt, from which some near-Earth objects originate. So basically, some of these asteroids are actually kicked out of the asteroid belt, essentially, and they have an orbit that intersects with other planets in the Earth. So it is believed that the HEDs come from the Vestoid family of asteroids. So, we are proposing the meteorite name Gqeberha. Sorry, my mouth is a little dry, I didn't get that click right. Gqeberha. That is the new place name of former Kirkwood in the Eastern Cape Province. We say it's proposed because we still have to classify the meteorite and then present the classification and the name suggestion to the Meteoritical Society's Nomenclature Committee. And, you know, I want to reiterate that really, you know, again, we've only had this meteorite a few days, you know, so there's a lot more science to come. So stay tuned. And my colleagues are now going to show you the meteorites. We're going to take them out of the desiccator where they're protected from moisture, and we are going to lay them out on the table. Please don't touch them. We're going to take a bit of time to unpack them, so please be patient. And then after that, we are going to turn over to my colleague to describe some of the further science that's going to come.
Christine and Francis are with us in a couple of minutes.
Would it help if I put it down on the foil?
Please.
Yeah.
Everybody will be able
I
to
think we
take
can-
photos afterwards.
We can
Carry
continue
on,
and
and then
let us finish and then
we can finish, and this will be out, so everyone can take photos afterwards.
All right. Everybody will have an opportunity to look at it from close just now. And for now, I'd like to introduce Dr. Leo Vonopartis, who will explain to us some of the science that we will be done on these samples and what it's going to tell us.
So now that the excitement has decreased a little bit, the sample will remain out, and everybody will be able to get a photo, a nice clear photo during the interview stage. So I'm going to take over after Dr. Van Niekerk, and I'm going to speak about, or rather just summarize a whole lot of information that we've been presented here today, and then where we're going to go from here onwards. So, in brief, in a summary, how did we get here and where we're going to go? So, as Professor Gibson and Dr. Van Niekerk have described, in the beginning there was cosmic dust, meteoroids, other planetary material, all circling as the solar system was forming. They started to clump together, agglomerate, and form bigger and bigger bodies. Some of these bodies got so large that melting was possible, and you started to develop things that have crust, core, and mantle, so differentiated bodies. And as was previously shown, this is what some of them look like today. So this is for Vesta, one of the largest asteroids, and is found in the asteroid belt. And meteorites that come from these type of bodies are called Vestan or Vestoids or HEDs. So from this big rock in space, how does it come to Earth? Well, as previously alluded to, something else hits it, causes an impact, and then stuff gets flown around. Sometimes, if we're very lucky, one of those pieces will make its way onto Earth. And that's where we find ourselves. So that's what happens in space, but how we see it is something like this, which is a lovely bolide, and why we are all here today. And what's just been revealed, we have some, which is very uncommon, as you've heard. A lot of the stuff gets lost to the ocean, a lot of the stuff falls into places where people don't see it. So having a sample, especially something with a story of as it fell, it was picked up, is incredibly rare and very, very exciting, both for the South African people, international community, international scientists, and South African heritage. So we've caught the car. Now what? So it's very simple. Dion has alluded to what we've done so far. We've done the macroscopic, or the large type of identification of minerals, looking at textures, the color of the sample, any of fractures, grain sizes, stuff like that, stuff that we can record and describe from the sample, the hand specimen that we have. Then we've weighed the sample, so we've got its mass. We can then do its density, and we do magnetic susceptibility. These are all physical properties of the sample, and we do this on as much of the material as we can get our hands on. After which, we have to make a thin section. So the two pieces of glass on the right-hand side. A little bit of material is consumed to make these very, very, very thin pieces of rock. They're sliced so thin that light can shine through them. And we use that on an optical microscope in order to identify minerals, look at shock, look at any alteration that has occurred on the sample. And this is an example on the bottom left of a chondrule in one of these thin sections that Roger has spoken about. So we do all of this in the beginning to get a firm understanding of the mineralogy, to get an understanding of what we're looking at. After which, seems to not have a photo there, but it's okay. We look at the chemistry or the geochemistry of these samples. We'll move from optical light, so using visible light to look at the sample, to something like a scanning electron microscope, which uses electrons to look at the sample. This is used to obtain chemical compositions of minerals. We can use the scanning electron microscope, or SEM, to get modal abundances, so how much of different minerals are in the sample, and map the thin section for future analysis. So to the right of the photo is a map of a sample thin section created by one of these instruments. After which, we'll use something like an electron microprobe, which is microscopic in situ, so in-place analysis of minerals. We can get chemical compositions which are vital for us to classify this rock effectively and accurately. After which, we can also do isotopic analysis. In this case, oxygen isotopes are very vital and very useful for us to fingerprint where in the solar system this rock may have originated from. So, taking all this information, we need to officially classify this rock as a meteorite. And how we do that is we compile all the data that we've collected, so the descriptions, the physical properties, any chemical compositional data that we have, as well as the mineralogy. We put that all together and we combine it and we send it through to the Meteoritical Society, to which they vet and review our data, and if they agree with our proposed name and our proposed classification of the rock, they're certified, and then it becomes an official meteorite in the database of meteorites. Gibson has said sounds like a lot, but in reality, very, very little amount of material exists. So after we've gotten the formalities out the way of classification, we can then do lots of other things. We can throw the kitchen sink and stuff like this. But it all depends on what the chemistry shows us and what we actually have available to work with. So stuff that we can do is we can use other type of isotopes to start to understand how these vestoid bodies or asteroidal bodies have formed, maybe the ages of the formation. We can use stable isotopes, again, to fingerprint where in the solar system, which asteroids or other bodies these meteorites come from. But not only about the parent body itself, we're also able to tell things about the time it is spent in space. So between its parent body and landing on Earth. We can use noble gases, and don't worry about the big names, but the other cosmogenic radionuclides. Essentially what they're looking at is how long it was exposed to space and the radiation in space. and we can also get approximate size estimates of what the meteoroid was before impact on Earth. So we can refine, as we already have, from car to motorbike to an actual proper estimate of what the meteoroid body was before it impacted Earth. But this all depends on what we find in our initial analyses, and that will guide us on our way forward. So that's a summary of how it's come to us and where we plan on going. So watch this space, and we hope to be able to update you as we get more information.
All right. Then you welcome back Professor Gibson for a little bit more presentation and a Q&A session after.
Thank you. So I said I would bookend it, and so here I am. It's coming to the end. Firstly, we've just spoken about how busy we've been. I think we're probably averaging 3-4 hours sleep a night most of the time. People are driving large distances. We're running around. We're trying to catch people when they can talk to us and collect information. We're trying to do the science as well. But none of this would have been possible if there weren't a whole lot of other people who are getting very little sleep. And that includes the media teams from the 3 universities. So thank you to Prim, to Christelle and Sharona for getting everyone motivated and working really hard to make the event happen, to get the press releases out and so on. Particularly to Skulk, who I think really needs more sleep, because he's been working on this literally from when I think I phoned him on Sunday evening to say we need to get a press release out. So thank you for that. Also, thanks to the Eastern Cape Provincial Heritage Resources Agency for reacting so quickly. As we've said, we don't tend to move very fast in the geosciences world, but when it comes to heritage, you have to, and we need the permission of the Heritage Resources Agency to do that. So thanks so much for all your activity and bringing the team together and helping us with that. Also our support staff at our various universities and departments, who not only have helped us deal with the emergency, getting bookings of vehicles, etc., but actually they're going to become important in the time to come with the processing of the samples. The other thing is to thank Professor Chentu for hosting us and agreeing to host us. And unfortunately, Dr. Mahed couldn't be here, but thank you to Dr. Tenelia for standing in for him and chairing. And then the unseen people, the astronomers, Peter Hurst particularly, and Tim Cooper, as well as Daniel Kunama, who are really behind the scenes doing all the hard maths while we show you the rocks. Thanks to them. But particularly what the team wants to say is thanks so much to the people of the region and other regions who have been so good about sharing. And the online, this is our first online event. We had a little bit of a one in 2018, but it ended up in Botswana. But this is really showing what we can do if people are alert, aware, informed, and start to communicate. So thanks for that. And among those, the superstars. Sorry, it's quite something to see. Elise, for what you've done, for being so alert. And to the team from Cape Point, the team. It was definitely a team effort. The sharp eyes of Stephen, the amazing reflexes of Zoe, the analysis of MCA, as you put together that light show and that sound show that actually helped us to know what we were dealing with. And again, we're asking if people can continue to contribute. If you've seen something, just be honest about what you saw. It's not about being impressive or anything. It's just the honest opinions that we actually get to see. So that's my formalities out the way, and it's my job then to put it all together for you. It is only 218 and a half hours since this event happened. It's phenomenal what we've managed to achieve in this age of social media. Initial social media reports were confused and varied. It was a gas explosion, a nuclear explosion, an airplane crash, space junk, landslide, rockfall, earthquake, And of course, the aliens featured very prominently in the J Bay area. So thank goodness for that indomitable South African spirit. But some were spot on. Some immediately, when Jessica posted and said, I think this might be a meteorite based on Elise's report. And people came in, and quite a few people were saying, yeah, looks like it. Better get it to the heritage authorities. So we're informed. So let's put it all together then as a wrap-up. So we're going to break it up essentially into phase one, the visual side of it, what we call the luminous flight stage. And what we see here is this little sketch of what a typical bolide event should look like. So somewhere at about just before 8:51 a.m., this object, which has been in space for tens, millions, hundreds of millions of years, coming from the dawn of our solar system, encountered Earth's atmosphere. And as it did so, it came in over the coastline, moving in an east-northeast to northeast direction, traveling at 20 kilometers or so per second. And it crossed the coastline somewhere between Gqeberha and George. The object itself was probably closer to 1 meter than 1.5 meters based on the spectroscopic analysis that Tim is computing. We're hoping it's bigger. We geologists always hope that the rocks are bigger. Let's see. Maybe we'll get to our bubble car size at least. As it penetrates deeper into the atmosphere, the denser atmosphere caused more friction, so it starts to glow and ultimately melt as it heats up. And it starts to lose mass, and that's the tail of light that you can see behind it, the hot particles being pulled off it by this incredible speed. And it reduces its volume. The supersonic speed, of course, is creating a shock wave, a Mach wave, a sonic boom that's passing out. But in fact, the meteorite is moving the object is moving so fast, it's outstripping the sound wave at this point. So the boom is lagging behind already.
Just deal with
and
I believe are the most.
Then at about 38 kilometers altitude, it meets its match. The atmosphere is too dense, or the fracturing within the object is too large. Gases are getting in from the atmosphere under this incredible pressure, and it literally heats, it's hot, so it explodes. Stephen notices that. Zoe reaches for her camera and records the final phases of the luminous flight, which her metadata then give us the actual time of the final end. So probably 5 to 10 seconds before that is that whole history before Zoe starts to record it. And then, of course, after that, we enter the dark flight phase. So everyone thinks, wow, those were lights. Well, was there any smoke? No, let's get on with our lives. And 3 or 4 or 5 minutes later, there's this massive rumble of thunder, maybe accompanied by massive sonic booms, windows rattle, the ground shakes, doors rattle, and literally people can feel the vibrations through their feet, as MCA did on that sand dune as they were looking at it. And this is happening at the same time, the remaining particles, whatever's left, we hope it is more than this, but we have to find it. It should be more than that, but can we find it? And those particles are drifting down, initially on the flight path, straight line, and then they start to slowly feel the force of Earth's gravity, and they start to droop down on a parabolic curve. And there's a lot of maths that will go into calculating then where they actually end up. But they spread out. They don't all land in a lump. And by about 9 o'clock, so less than 9 minutes later, all is quiet again, except for that sound wave that's traveling all the way through the upper atmospheres, the infrasound, heading to these nuclear test ban treaty stations like the one near Boshoff, where they will record the event and where scientists will then be able to detect it. So let's just put it all into perspective then. Is it an unusual event? Yes and no. The event is the 20th that is recorded on the database for this year, so it's little under one a week is occurring, and you can see them. And in fact, ours is one of the smallest of 2024, so we didn't quite make the top 3. But it still released 92 tons of energy, as light and as sound energy and explosive energy. It's one of only 3 bolides that have been reported over South Africa in recent times, but probably some of our other falls, our other 21 falls, have actually been associated with bolides. And the point is that the others, including the one in 2009 that we saw in Gauteng, were much, much larger. And that gives us pause for thought. We know that the meteorite appears to be a relatively rare HED type, achondrite breccia. If we find more pieces, we might find different types of rock within that because it's a mishmash. So we hope to find more. And so to wrap up then, we've seen that there's an event that was much, much larger, 18,000 tons of TNT as opposed to 92, so many times more, that occurred over the Limpopo region and southern Zimbabwe and Botswana in 2009. But that's not the end of the story, because just a little over 11 years ago, in February of 2013, over the Chelyabinsk region in Russia, there was a 17 to 20 meter asteroid that came in as a bolide. It generated 440 kilotons of energy, which is about 20 times larger than the nuclear weapon that was used on Hiroshima at the end of the Second World War. It destroyed over 100,000 square meters of glass in 6 cities. That's the blast wave. So be thankful that the windows only rattled this time. Caused over 500 million rands worth of damage, and nearly 1,500 people were injured, mostly by flying glass as the windows blew in, but others by broken limbs falling on the ice because of the force of the air wave knocking them over, and even UV burns caused by the fact that the bolide was 30 times brighter than the sun, the energy released. So, to bring us all back then, what if? Could it happen again? What if? Well, it's happening all the time. Here's an example. Note the posts from the Western Cape only 5 years ago now. There's a bolide in daytime. It was spotted. It was on the news. Chelyabinsk, of course, was a disaster. So that bolide was about the same size. Well, it was about 10 times larger than the one that happened last week. Chelyabinsk, of course, was massive. But Chelyabinsk is only the middle part of a spectrum, because sitting 40 kilometers north of Pretoria is the Twying meteor crater. That is a 1 kilometer wide crater that probably was a 10 megaton explosion. If that crater, it happened about 220,000 years ago. And at that time, we know from the cradle of humankind that we have species like Homo naledi walking around. I'll probably get into trouble for saying this on international media, but Homo naledi must have witnessed the largest meteorite event that has possibly been hit the Earth since the dawn of our species. And yet that pales into insignificance to the Vredefort Dome near Parys and Vredefort in the Free State, which is the largest meteorite impact scar we have. So, to wrap it up, thank goodness our atmosphere protected us. This wasn't a particularly big event, but it was big enough to cause significant disturbance. It is a taste of what is possible when these rocks come in. We are, as a community of scientists, working to understand not only the rocks and their history and our origins in the solar system, but we're looking to understand the threat that these things pose to us, because they pose a continuous threat. 100 to 200 tons a day is coming in. And at the moment, there is a global network of cameras monitoring this. South Africa is part of that. There is a global network of telescopes trying to find these objects in space. There are millions of them. We are nowhere near being able to detect 1 or 2 or 3 meter-sized objects with any regularity. We're still up. We don't even get the 100-meter diameter objects yet. But there is an effort to actually find a way to protect us against this. And the information that we are presented with here, the observations, the eyewitness reports, and the scientific calibration of those reports is an invaluable tool that will be read by scientists around the world as we continue to try and understand these phenomena and our way forward within them. So thank you very much for attending, and thank you for listening to us, and thank you to everyone for participating. Nicholas, I'm supposed to kind of sit here and see if there's questions and answers, but I'd like the team to come up and sit, and we can just see what you do. I don't know what the time frame is, how long we've got. Prim? Is Prim around? 10 minutes, okay. So, I don't know if anyone's monitoring international or not. So, questions? Do we have to have a